So mark your own. Here we go. Be honest. I saw several blank quizzes. Give yourself the 0. Don't try and lie your way through this. As I wandered around class. Stream of protons is acted upon by a magnetic force of 5.8 newtons, 5.8 times 10 to the negative 14 newtons, while traveling perpendicular to a magnetic field at blah, blah, blah. What speed are the protons traveling at? So if we're talking about forces, we either have the force on a wire, which is not what this question is talking about, or we have the magnetic force on a charge. Now, they do have to be perpendicular. If it's traveling parallel to the magnetic field, it will not feel a force. This is straight plug and chug, except they want me to find the velocity. So I guess the speed is going to be force divided by QB. It's going to be force 5.8 times 10 to the negative 14th divided by Q. Oh, proton. They don't need to tell me the charge. Magnetic field, 0.06. No, not 0.06, Mr. Dueck. 0.6, Mr. Dueck. How big is the force? Let's find out. (5.8) negative 14 divided by 1.6 negative 19 times 0.6. You get, how big is the speed? 6 let's see, 1, 2, 3, 4, 5. You get 6.04 times 10 to the 5th? Meters per second. Question 2. A wire is carrying a current of 5.2 amps as shown in the above diagram. If the force that the wire experiences, what is the strength of the magnetic field? So I'm going to use the force on a wire. They want me to find the strength of the magnetic field. Symbol for magnetic field is B, which is going to be F over IL. The force is 2.4 times 10 to the negative 2 divided by the current is 5.2. Ah, which length? They gave me 2 lengths. Which length? The length of wire that's inside the magnetic field. Wire here is not undergoing any force. It's not being affected by the magnetic field. It's the wire from here to here that's being affected by the magnetic field. 0.042. 2.4, scientific notation, negative 2, divided by 5.2 times 0.042. I get a magnetic field of 0.11 Teslas, or 0.1, well, I guess no, 0.11 Teslas. Is that right? Fairly big. We said a magnetic field of like 5 Teslas is huge, so 0.1 is 1/10 of huge. Oh, direction. Let's see. Current traveling that way. Magnetic field into the page. Right-hand rule says down the page. Number 3, an electron traveling at 6.2 times 10 to the 6th meters per second moves perpendicularly to a magnetic field of strength that. What's the magnitude of the force? Okay. This is straight plug and chug. 1.6 times 10 to the negative 19. V, 6.2 times 10 to the 6th. B, 8.5 times 10 to the negative 3. 1.6 negative 19 times 6.2 to the 6th times 8.5 negative 3. You get 8.43 times 10 to negative 15. Units, it's a force. Newtons. By the way, what are the units for magnetic field? Teslas. The electron is forced into a circle by the magnetic field. I like this question. I like this question. I like this question. Well, now what we're saying is the magnetic force equals the centripetal force. What we're saying is QVB equals mv squared over r. Hey, we're even saying one of the v's cancel. We get this. QB over m equals mv over r. Hey, by the way, just as a quick final exam near the end of the year review, what's another word for mass times velocity? Yeah, actually, it's you may sometimes see this written as momentum divided by the radius, because that is the momentum, for what it's worth. In fact, you could say that the momentum was equal to QBR, even though you didn't know the mass or the velocity. You can actually find the momentum, strangely enough. Anyways, what do we want to find? Oh, R. R equals mv over QB. Mass, electron, 9.11 times 10 to the negative 31. Speed, 6.2 times 10 to the 6th. Q, electron, 1.6 times 10 to the negative 19. B, 8.5 times 10 to the negative 3. Radius of this would be what will the answer be? I can hardly wait. You get 4.15 times 10 to the negative 3? Not a very big radius. I made up lousy numbers. What's the kinetic energy? Hey, some review. What is kinetic? Kinetic energy. That's been the same all year long. A half mv squared. 0.5, 9.11 times 10 to the negative 31. V squared. 6.02 times 10 to the 6th squared. .5 times 9.11 times 6.2 squared. You get 1.75 times 10 to the negative 17, or did I type that wrong? Is that right, Brianna? Sorry? You didn't square it? Oh, what a great time to make that mistake, because you won't on the final exam, right? And of course, I would write in huge letters, squared, and I would freak out on you. Is it 1.75 times 10 to the negative 17? By the way, while we're units, joules, while we're reviewing, before you put this away, where'd that energy come from? Probably through an accelerating voltage. You could probably actually say, for what it's worth, Q voltage equals 1.75 times 10 to the negative 17. A nice extension question for the final would be, hey, what voltage would you need to get it going that fast? Divide that by the charge, well, divide this by 1.6 times 10 to the negative 19. I would need to send it through 110 volts. I could do it with a plug. Number 4, what's the magnetic field strength inside a solenoid? Oh, okay, magnetic field inside a solenoid. We said that the magnetic field in a solenoid was mu naught N I over L, where mu naught, Andrew, was the permeability of free space. My favorite constant sounding name. Sounds great. And it's 4 pi times 10 to the negative 7. N is the number of turns, 600. I was the current, 4.5 amps, all over 0.032. 4 pi, scientific notation button, -7 times 600 times 4.5 divided by 0.032. You get 0.106 units, Teslas. Give yourself a lovely score, please, out of 13. However, I don't want to collect the quizzes. I want you to have these to study from. So if you could have the person on the end of each row write their score on a piece of paper. Just a little reminder, if you go to my website, pitmath.com, click on Physics 12 links. Joel, you want to watch this, please, my friend? And if you click here for some tutorial videos, I do have a tutorial that I guess I did last year or the year before. I am going to be around tomorrow after school. Come and ask me questions from the review. I'm not going to be doing a formal running through the whole unit in one show, but I'll be around tomorrow after school. Okay? Test next class, Thursday. Please make sure you show up and bring your stuff. Lesson 1 in the next unit, which is actually part of the same unit. Magnetic forces is one big unit worth 18%. I split it up into 2 mini units worth 9% and 9%. Basically, in this second half, we'll be looking at in the first half, we asked how do forces affect magnets. In the second half, we're going to ask how do magnets affect currents. Lesson 1, voltage induced by motion. In the previous unit, we learned that when charges move, they produce a magnetic field. We said that when you run a current through a wire, you point your thumb in the direction of the current and your fingers curl in the direction of the magnetic field. Or if you combined it in a solenoid, you held the solenoid in your hand, curling your fingers in the direction of the current, your thumb pointed north. We said that a moving charge, a current, can induce or create a magnetic field. In addition, a magnetic field will exert a force on moving charges. Well, early in the 19th century, scientists such as Michael Faraday in England and Joseph Henry in the US were aware of these properties, and they both asked the obvious question. They said, look, if a current can produce a magnet, can a magnet produce a current? If a current can create a magnetic field, can a magnetic field create a current? Recall, electromotive force, or abbreviation EMF, that funky E, it's an archaic word that refers not to a force, but to the voltage of a cell. So voltage and EMF mean the same thing, and these symbols are going to be used interchangeably in this unit. Here's what we want you to imagine. Suppose a piece of wire moves through a magnetic field. Because the wire has electrons in it, charges, and they're moving, they will experience a force. The electrons are free to move around, the positive nuclei are not. The negative charges will move to one end of the wire. We're going to use the right-hand rule. Now, even though we're knowing that electrons move, we're going to pretend that positives move to make our life easy. So zoom in on this picture right here. By the way, this is supposed to be a magnetic field into the page, so you can just kind of go like that if you want to. And we want to look at one charge, one positive charge sitting right there. See him? This is a metal bar, and somebody is just moving it with their hand. Or we have some kind of machinery moving it. Or it's getting pulled on a string. I don't know. I don't care. I just know, Brandon, it's being moved. Which way is this charge moving? Down. So that's its velocity. Can you all point your thumbs in the direction that the velocity of the charge is traveling? Point your thumbs down the page. Which way is the magnetic field? Into the page. So extend your fingers into the page. Which way will this positive charge get pushed? To the... Okay, this end of the bar is going to become hugely positive. And this end of the bar is going to become hugely negative. You may not realize, but what we've just done is we've separated charges. We've created a battery. We've induced a voltage. See it? We've induced a voltage. We've separated charges. Voltage is defined as energy per charge. We've done work on the charges. Since we've separated them, they want to come back together. That means there's energy that we can use. We can bleed that energy off. It's similar to lifting something up high and then dropping it. We call this voltage induced by motion, or motion voltage. Since the energy is, in this case, not from chemistry, like in a Duracell, but from motion, we call this an induced EMF. In other words, motion can induce an EMF, a voltage, and create a voltage. Find an expression. Well, we said this. Voltage was potential energy per charge. Voltage is force times distance per charge, because potential energy is how much work, energy is the ability to do work. Also some nice review, work is force times distance. Which force? Well, magnetic force on a charge. Voltage is going to be, now magnetic force is equal to QVB. So I'm going to stick that in here. I'm going to get QVB times D divided by Q. And now you'll notice once again I'm putting wings on my voltage because Mitsu, I've got V voltage and V velocity. I don't want to get it mixed up. Uppercase V and lowercase v. Hey, what do you notice about the Q's? This is going to give us our equation for voltage. It's going to say this. The voltage, but because it's an induced voltage, we tend to use the archaic symbol EMF. This is what appears on your formula sheet. It's equal to BLV, where L is D, the length of the wire. V is how fast the wire is moving, and B is how strong the magnetic field is. This is how you can create current. This is how generators work. So generators add a rotating system, which makes it a bit more 3D complicated, which we'll talk about later. Oh, but one more thing. All three of these need to be at right angles to each other. The length needs to be perpendicular to the magnetic field, needs to be perpendicular to the direction that it's traveling. If they're not perpendicular, we get only a small amount of voltage. In fact, Sean, we essentially get zero. I'll show you why in a second. Example 3. Here, turn the page. What direction is the magnetic field here? What does it say in the picture? Into the page. What direction is the velocity? Down the page. So those are at right angles to each other. Ah, but Emily, what direction is the length? Also in the same direction as the velocity. All three are not perpendicular to each other, and I'll show you why you get so little voltage. Let's look at our little tiny positive charge right here. Which way is he traveling? Down the page. So as practice, point your thumbs down the page. Which way is the magnetic field? Into the page. Which way will he get pushed? To the... How far can he travel, though? If this is a thin wire, barely anywhere. Yes, you're going to separate positive and negative charges, but like barely, Katie. Nothing. You're not going to... Nothing. You want the wire to be this way, and you can put some distance between them, and now they want to come falling back towards each other, and now you can get them to do some work. Okay? So this would become positive, this would become negative, but there's so little distance between them, Andrew, that, nah. Very little EMF will be induced. That's a classic multiple choice question. They'll give you 4 diagrams and they'll say which of these would give you the biggest voltage. I guarantee in 3 of the diagrams, all 3 magnetic field, length, and velocity, aren't perpendicular to each other. In one of them it is. Or maybe in two of them they are, but one clearly has a bigger length or something. So, find the voltage induced by motion across the ends of a moving wire and indicate the polarity. So, this is my stick figure diagram. We have to translate this just a little bit. Which way is the magnetic field according to this question, Katie? Down the page. The length is horizontal. Which way is the velocity? What does this little X mean? We need to know this symbol for the final and for your test on Thursday. What does that mean? Okay, so point our thumbs into the page. Let's get the direction first. Magnetic field down the page. Which end of this bar will become positive, the left end or the right end? Kara. How many volts? So this is a bar that's 80 centimeters, about yay long. Magnetic field of 1.25 Teslas, fairly strong. Velocity 5.25 meters per second, not very fast. The EMF is going to be BLV. It's going to be 1.25, 0.8, 5.25. All of you get your calculators out. So you're participating along with me. And ask yourself or calculate what the voltage is. How many volts? Can we maybe start getting it out before class? It would help. Do you get 5.25 volts? So where was this used? Well, believe it or not, airplanes can generate a voltage because airplanes are traveling perpendicular to the Earth's magnetic field. When you're nice and high up, basically there the magnetic field is fairly vertical because it's already starting to curve back to the Earth. Here's an airplane. Here's the velocity, and we're going to assume the magnetic field is downwards. The magnetic field is into the Earth, heading back down. The voltage is equal to BLV. Magnetic field of the Earth varies from, but we're going to say we're close to the North Pole, so 0.08. Which length am I going to use? The length that is perpendicular to the magnetic field and the velocity. Am I going to use the 150 or am I going to use the 60? The 60. And the velocity of 320. Katie, how many volts will we induce here across this airplane? How many? 153.6? This is what they actually, back on smoking flights, used to run the cigarette lighters, the pop-out ones, off of. And I think they still do run some appliances off. It's there. You're creating a voltage, why not use it? What was it? Sorry, 154 if I go to 366, 154 volts. Enough for a plug. Enough for a plug. Now, it's not free energy. That energy is coming out of the jet fuel in the long run. Okay? But, still, there. Now, all we're doing right now, Kara, is creating a voltage by separating the charges. What if we want to get a current flowing? Well, then we need to actually have a circuit. So what we're going to do is we're going to take that moving metal strip, and instead of just moving it through the air, we're going to slide it along two pieces of conducting rail. Like this, where this whole thing underneath here is metal, and we're going to slide it sideways. Okay, folks, I want you with me in the back row there. I don't know what's going on, but I need you with me. So if we connect the moving metal strip to conducting rails, the strip will act like a battery and we'll get current flow. So this thin wire here is a conducting rail. We put a resistor so that, Trevor, we don't have a short circuit. We don't want that. Here's our positive charge sitting right there. Which way is it moving? To the right. So point your thumbs to the right, please. What does this question say? Which way is the magnetic field supposed to be? What does the diagram say? Out of the page. So extend your fingers out of the page. So boom, boom. Which way is the positive going to get pushed? We're going to get a current flow. We're going to get a current flow this way. And we're starting now, Joel, to approach the physics behind how a generator works. One way to do a generator is to actually slide something sideways. Now, a better system is to turn a crank to rotate it, and we're going to talk about that in a couple of days, but it started here. It said, you know what? We're getting the voltage. In fact, you could make an argument, Andrew, that this is the same as a battery like that. It would light up a little light bulb here. I have somewhere, and I'll dig it up for next, no, not for next class. Next class is your test. I'll dig it up for the class after this. I have a flashlight that you shake back and forth, and you're literally, I think, doing this and inducing a current. Okay. Ah. Now it gets complicated. Okay. Kara, do you agree with me that if we pull this, let's say with a string, that these charges are going to experience a force that's going to push them downwards? Yes? Okay. Suppose, Kara, you were the one tugging, and you started to tug with the string. Okay? Thereby inducing a current. You would suddenly feel something pulling back at you, not the mass of the bar. You would feel a mysterious force pulling back at you. Why? Well, now, not only are the charges moving this way, but we've got them moving downwards inside the bar. We have a current going this way. So all of you, now point your thumbs this way, downwards. Which way is the magnetic field? Still out of the page. So extend your fingers out of the page. Which way will the bar experience a force? In the opposite direction of the tug. You would feel some mysterious force pulling back against you, and the harder you pulled, the harder it would pull back. Because, Andrew, you can't get free energy. Otherwise, we could just somehow give it a tug and it would just keep going. No, nature says, nuh-uh, I'm going to resist you. We don't get free energy here. So, if there is a current flow through the moving metal strip of wire, now there's also a magnetic force on the wire that tends to slow it down. For the current direction indicated, show the direction of the force on the moving strip. That way. That way. Resisting, Emily, your attempts to pull it. You would still be able to pull it, but you would go, there's something invisible tugging against me. No, it's not. It's nature saying you don't get energy for free. It's the right-hand rule happening because not only were the charges moving by you pulling them, once they started feeling that force, they started moving in a circle. That's also a different type of movement. Next page. Example 8. Okay. The strip below is 12 centimeters long and is moving at 4.7 meters per second. The external magnetic field is 0.08 teslas, and the resistance of the rail circuit is 0.25 ohms. 0.025. You know what? Let's label this here. 0.025 ohms. What's the first thing they want me to find here, Sean? Induced voltage is BLV. Magnetic field 0.08, and we could create that magnet with an electromagnet solenoid, or it could be a permanent magnet. The length, it says the strip is 0.12 centimeters long, moving at 4.7 meters per second. many volts will we be inducing? You always mess up? Don't do that on the test or the exam. Squared when necessary. Brianna, what'd you get? Still typing? .08 times 0.12 times 4.7. How about 4.5? Let's go 0.045 volts. 0.045 volts. Not a big voltage. How much current? Well, let's see. Do I know the voltage? Yeah. Do I know the total resistance? Yeah. Oh, hey, this is great review from last unit. How can I find current if I know voltage and resistance? Ohm's law. V equals I times R. I think that's really going to be I equals V over R. 0.045 divided by 0.025. How many amps of current do we have going? .80 amps? Actually, that's not a bad little amperage there. You get a shock. What does C want us to find, Trevor? Oh, force on a wire. What's magnetic force on a wire? By the way, you might want your formula sheet in front of you if you haven't got it already, because that would help you keep all this straight. And this C is fair game for your test Thursday, which is why I always do this lesson before the test, because it's nice review. What's magnetic force on a wire? What? Oh, Bill. Yeah, good old Bill. Let's see. Do I know the magnetic field in Tesla's, Mitchell? I do. Do I know the current? Yeah, and I figured it out, and I would say I like this question for the next unit test. Nice combination. Also, look at that. We're even reviewing some circuitry. Lots of good stuff here. Current is 1.8 amps, and the length was 0.12. How many newtons of force would you feel pulling against you? Uh, 1.73 times 10 to the negative 2. Not a big force, but you feel it. What if you went faster? What would happen to the voltage? If this got bigger, what would happen to the voltage? Nicole. It would increase. Nicole, what would happen to the current then? It would also increase. What would happen to the force that was pulling against you then? It would increase. Faster you go, stronger the force. Don't go anywhere, force is 0. But you're not inducing any voltage and not inducing any current. In fact, eventually there would come an equilibrium point when the force that was tugging in the opposite direction would match your force, and you couldn't go any faster or create any bigger voltage or create any bigger current. The next thing that Faraday asked was this. He said, well, instead of moving just a single bar, a piece of wire, what if I coiled the wire into a rectangular loop? Would I still get a voltage? Do I still get a current? So he said, well, let's look at a charge. Let's zoom in, Mr. Dueck, so they can see. Let's look at a charge on the front, right there. Which way is that charge traveling? Sorry? To the right? Point your thumbs to the right, please. Which way is this magnetic field, according to this question? out of the page, which way will that charge there feel a force? Which way will it get pushed? So it's going to get pushed downwards. Brianna, let's look at a charge over here at the back end. Which way is it traveling? To the right. Which way is the magnetic field? Out of the page. Which way is the charge at the back end going to feel a force? Also down? You know what we have? We have two batteries that are pushing against each other. This is like going up a chairlift and down a chairlift. You know what your net height increase is? 0. Oh, and what about right here? Well, this would also be experience of force down, but that's in the same direction as the motion. You know what? You can't separate charges in the wire. There's not enough distance. It would not induce any voltage in these two sections. It would induce voltages in these two sections, but they're in the same direction heading towards each other. You get a net current of 0. And he went, rats. Would have been nice. The voltages in each vertical section of wire cancel each other. So Faraday had hooked this wire, this rectangular coil of wire, up to a voltmeter, and he was moving it around inside a magnetic field, and the needle on the voltmeter wasn't moving at all. But Faraday was a great experimentalist, a very good scientist. As he pulled the wire, he left everything hooked up. As he pulled the wire out of the magnetic field, he saw the needle jump. What? He put it back inside the magnetic field. He moved it around. Nothing. As he pulled it out of the magnetic field, the needle jumped. What's going on here? Patience. Okay. Connor, in the previous examples, we supplied the motion to get the voltage. Now we're going to say, what if we supply the voltage? This is what we call a railgun. If you've ever heard the term railgun, Iraq was trying to build one a few years ago in the first Gulf War. This is what they're talking about here. This is an electric gun that can cause something to go really, 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 really fast. How fast? How big's your voltage source? Hook it up to a nuclear reactor, you're going really fast. How does it work? So in this circuit, Connor, the wire strip is initially at rest, and there's a power supply there. So current is traveling in this direction. First of all, what does A want us to find? Matt. Okay. Induced voltage is equal to BLV. What's the velocity of this bar right now, Matt? So what's the induced voltage right now before we start anything going? 0. What is the direction of the current? Well, the direction of the current is that way because of this battery. So Andrew, when we flick this battery on, boom, oh, we got a resistor so we don't short out the battery. When we flick this battery on, charges are going to start moving upwards in this bar. So Katie, can you point your thumb, can all of you point your thumbs upwards? Great right-hand rule review. No, up the page. Brett, follow along with me, right? This way. Which way is the magnetic field? Out of the page. So thumbs this way, magnetic field this way. Which way will this bar experience a force? It's going to feel a force that way. You know what's going to happen? It's going to start to accelerate. This is your railgun. It's going to start to speed up. It's going to start to go faster and faster and faster and faster and faster and faster and faster. Problem. Okay? So this was the situation right when Brett flicked it on. As it speeds up, what happens to the induced voltage? Well, the induced voltage is BLV. As V gets bigger, as it speeds up, Nicole, what happens to the voltage? Okay. What happens to the current? Well, first we need to zoom in here. So here's our little positive charge right there. Now it's getting pushed upwards by the battery, but now it's also traveling sideways. So we use the right-hand rule, pointing our thumb upwards, Katie, at the very beginning here. But now it's also moving sideways. So point your right thumbs sideways. Which way is the magnetic field? Out of the page. Which way will the positive feel a force once this bar starts moving? Down against the battery. It's going to feel a force that way. What's that going to do? Well, if you have some current going up and you have some current going down, what's going to happen to your net current? It's going to get smaller, and eventually it's going to hit zero. But it's going to get... because you got current pushing in the opposite direction against the battery. This has become its own little battery. It's like a chairlift pointing into another chairlift. This one's still probably bigger, but your net height change is smaller, so your net current is smaller because current is voltage divided by resistance. What happens to the magnetic force on the strip? Well, if the current gets smaller, what happens to the force? What happens to the speed then if the force gets smaller? Still, zoom out a little bit. Still increasing, but not accelerating as fast. It would take off like a shot, but the faster it went, the slower it would accelerate. Until Kara, there came a magic equilibrium point. You would maximize the V when the velocity was exactly inducing the same voltage as whatever your battery or power system was. So if you were hooking this up to a 1000 volt system, as soon as the induced voltage hit 1000 volts, it would now continue at a steady speed. You've maxed out your railgun. Does that make sense? And some nice review of right-hand rule stuff for your test next class. It says, explain your answer using relevant physics principles we just did. Some neat applications. Okay. The first has been proposed as a potential space station launching system. All right. So you could launch vehicles from the International Space Station without the need for rocket fuel. Oh, that'd be cool. How? Well, you have large solar cells to make the current. So instead of a battery here, think you're running it off those great big huge solar cells that the space station has. Is that okay, Trevor? Oh, and our magnet is going to be a couple of big electromagnets, a couple of huge solenoids, which would also run off the solar cells, Matt. Our conducting wire is going to be the space station, the spaceship, the space shuttle itself. Make it out of a conducting material, or just put a strip of metal along the bottom, like tin foil almost. Okay? What would happen in this setup here? Well, which way, right now our velocity is 0. Which way is the current moving based on the battery right here, Emily? Up. So follow it through, draw with me the current. Oh, which way will the current be moving through the space shuttle then? Down. Okay, point your thumbs down the page. Which way is this magnetic field? What do these X's mean? Into the page. Which way will the space shuttle experience a force? To the right. Ah, it'll launch with no rocket fuel. It'll slowly get pushed off these railings, and it'll speed up and speed up and speed up and take off. Very nice. By the way, what if I reversed this battery? Which way would it experience a force? Left. Wouldn't be that good, but bang it into the space shuttle. What if I had this current set up this way, but it came traveling in at this direction really fast? And now we're starting to look at how some of the new roller coasters have magnetic braking. They brake you using this force, which is great because there's no moving parts. It's very smooth, and as you slow down, the force decreases, so it brings you to a very smooth stop. The initial jerk's really hard, and it's easier. The other application is in electric motors, where a coil spins inside a magnetic field when a current runs through it. The coil experiences motion voltage, which is commonly referred to as back EMF. You're going to find out in a couple of days that any electric motor automatically acts like a generator, which is why an electric motor can only go so fast. When you hold a power drill down and you rev it as fast as it can, what you've really done is you've revved it up until the induced voltage that it's creating matches what's coming out of the battery or coming out of the plug. Okay? As this strip continues to speed up at a lesser rate, it's not accelerating as fast, the induced voltage will continue to grow. What happens when the induced voltage is equal to the supply voltage? Well, your net voltage becomes zero because they cancel each other out. And since I equals V over R, if your net voltage is zero, what's your net current? Zero. And since F equals BIL, if your current is zero, what's your net force? If there's no force, which of these must be true? A or B or C? Kara? A. Now, B would be wrong. It can't speed up. So let's cross that out. In fact, what it would start to do is it would slow down, Kara, a tiny bit slower than the equilibrium point, and now there would be a tiny net current forward again, and it would push it to that equilibrium. It would kind of, and then find the butter zone and continue going at a nice steady speed. But this is how a railgun works, Jacob. You want it to go faster? Throw a bigger power cell on there. The U.S. military has been experimenting with these quite a bit. It's nice because you have a way to launch something that you don't require fuel or propellant or an explosion. It's a much, if I can use the phrase, safer gun. Which sounds kind of weird. Example 13 says, find an expression for the maximum speed of this railgun. I would totally love to, but instead we're going to go to example 14. I'm pressed for time. It says, for each instance below, find the induced voltage EMF. Okay, let's draw a line down the middle of the page here. So the induced voltage, BLV. Find the induced voltage for the first situation. In your head, please. Sorry? 0. Find the induced voltage for the second situation. By the way, why is the first one 0? Hasn't started moving yet. Second one is going to be B, 0.35, L, 4.1 meters. V 8. Sorry? 11.5? Is that right? B says, find the net voltage. Well, in this first one, since there is no induced voltage, the net voltage is your battery. What's your battery? What's your net voltage over here? Well, it's 320 volts up, but let's just double check. Here's my positive charge. Which way is it moving now? To the right? Which way is the magnetic field? Into the page? Which way will that positive charge get pushed? I think it gets pushed in the like against the battery this way, yes? So I will have a net voltage. My net voltage is going to be 320, take away 11.5. Isn't it? 308.5? Someone double check me. Yeah? I'll keep the extra sig figs because I'm going to be using this. C, current and direction. Well, current is V over R. Current is V over R. What's the net voltage in this first situation? 320. Resistance, 8.5. $320 divided by 8.5. In this first situation, 37.6 amps. In the second situation, it's 308.5 volts divided by a resistance of 8.5. $36.3 amps. About 1.3 amps less. Connor, what does D want us to find? Okay, magnetic force. F equals Bill. F equals Bill. 0.35, 37.6, 4.1. 0.35, 36.3, 4.1. You get 54 newtons for the first one. 0.35 times 37. Yeah, 54 newtons. For the second situation, $52.1 newtons. Mitch, what would happen if this sped up? If that got bigger, what would happen to this answer here? The voltage, the induced voltage. What happens to your net voltage? Smaller. What happens to your overall current? Smaller. What happens to your overall force? Eventually you'll find an equilibrium point where the force, in fact, the equilibrium point is when this voltage equals that voltage. If you went 320 divided by that, you could find your maximum speed. Force a vector? Yes, it is, and they want direction. Let's use our right-hand rule to figure out the direction. Here, in situation A, the charges are moving, downwards based on the battery. So thumbs down, magnetic fingers into the page. To the right. What about here? Well, let's see. It's still moving to the right, into the page, moving up. This is also to the, I think it's to the left. Let me see. Boom, boom. No, not to the left. Come here. Magnetic force and direction. It's moving to the right, so it's getting pushed up. So the charge is moving up. So they get, yeah, you know what? It is to the left, and I'll show you why. Now, these charges are getting pushed upwards. So point your thumbs upwards, to the left. I'm not going to ask you this complicated a question, but it's a neat application. Yeah, force is a vector. Is that okay? There's two forces going on here. So first of all, what's the velocity of the bar? What direction? So point your thumb to the right. Magnetic field's into the page. That's going to push the charges upwards. So now not only are they moving upwards, they're also, sorry, to the right, they're also moving up. So point your thumb up into the page. Oh, they're getting, you would feel something tugging against you. You would feel a force tugging against you. Okay. What's your homework? Are there no questions attached to yours? That's going to have to change next year, Mr. Dueck.